This will be a whirlwind tour of flowing water as an energy resource. Um, I'm pretty sure you've already come to learn that water and power are tightly linked. And so a lot of energy is required to move and treat water and wastewater. So there's a coupling on that side. And of course, water is a very important element in managing excess heat at thermal facilities. And then the third piece is what I'm going to focus on today, which is the power available from moving water, since moving water is an energy carrier. So that's what I'm going to try to focus on today. So this is my agenda. It's ambitious, and so I'm going to move fairly quickly. Now, a number of the required readings and videos cover some of this material, so I'm going to try to move quickly and not repeat too much that you've seen, but I want to try to put it together into a whole picture. And so hopefully some of the things will be familiar and won't slow us down too much. I'm happy to take questions as we go along, and if I use vocabulary you don't recognize, you should stop me and let me explain my words. So what I want to cover are some fundamentals about power and flowing water and the energy transformations that we use. I think it is useful, and you'll see why, to inject a little bit of sort of history and context into water as an energy carrier or hydropower. And I want to situate that a little bit into the larger picture of energy systems and how hydropower facilities fit into energy systems, how they're operated in that context. And then I'm planning to have enough time at the end to get to Diana's fish and talk about some of the impacts and issues that are swirling around hydropower today and have been swirling around them for a very long time. Now, I find it convenient to sort of start by showing you where I'm headed. And so here's one way of framing what I'm going to be talking about. So on the one hand, I've listed a number of features associated with hydropower. And my goal is to build enough background so you can appreciate why I've listed those as features. Many people might think of those as benefits. And then on the other side, I've listed what I've called limitations. And as you can read what I have there, I'm going to explain a lot more. And then this is the impact part that we will get to. So this is where we're headed. And as I'll try to sort of move along fairly briskly to try to cover all of this in the time that we have. Okay, so the basic notion is that flowing water represents both a movement of mass and mechanical energy. So it's a flux of mechanical energy. And we represent that when we're talking about a fluid using this notion of head. Okay? And head is simply energy per unit weight. And it's almost always indicated by a little h, as you see there. And it has three components in general. Right? The gravitational potential energy associated with elevation, and that I'll always use a z for that. And then the normal force that's represented by pressure, which is just normalized by the unit weight. And so that's another potential energy, is one way of framing it. And then the kinetic portion of the energy is associated with this term that has the average velocity squared over 2 times the gravitational acceleration. So that's the kinetic energy velocity head. Okay? And so it's the sum of those three things that are the focus of what hydropower is all about. Now, this leads to a fairly simple notion of the power available in flowing water. And I've written it out here and sort of factored it out in a number of different terms. So power, which of course is energy per time, we can sort of factor that out into the weight per volume, the volume per time, and the energy per weight. So the energy per weight is the head, so that's the head. Volume per time, in my world, is the volumetric flow rate, and it's almost always indicated by a Q, okay? So that's the volume of water moving per time, and then gamma is just simply the unit weight of water. So what we have then in hydropower is about harvesting some of this energy, not all of it, or it would stop moving, and that would be a bit of a problem. So we harvest some of that energy and then transform that into electricity in general. Right? The other thing that this simple equation starts to hint at that I think is an important and a theme is that this shows why hydropower is so scalable. And we're going to see examples of that huge scalability of hydropower, because there's a trade-off between how much water is flowing by, the flow rate, and the head. So we can have the same amount of power with a little bit of flow and a lot of head, or a lot of flow and a little bit of head. And so hydropower has a scalability that plays a significant role in how it is in fact developed and distributed globally. Now, before we get into the details of how we exploit the power in flowing water, the ultimate energy source here is solar. Okay? So what we're looking at here is a little schematic of what most people call the hydrologic cycle. You've probably seen it in one form or another. The fact of the matter is that water is moving through the environment, driven dominantly by insulation. Differential insulation creates winds, but the basic energy transformations that are happening is solar energy is used to vaporize liquid and solid water. So it adds energy. And then at some point, that vapor is condensed and that energy is released. So there's an energy flux associated with vapor moving around through the environment. And so the typical cartoon, here we have the oceans or lakes, evaporation is occurring, winds then move that vapor, and the energy wash between evaporation and condensation is zero. So that balances. But the issue is that winds allow that vaporized water to end up at higher elevations on the ground surface. Okay? And so it's this water that is returning to low elevation after having been deposited from the atmosphere. That's the resource we're talking about. That's the energy flux that can be available. It has many, many roles in the environment and to humans, but that's what is available and what we mean by hydropower. Okay, so we've got our power equation, and the question is, how do we go about extracting some of that flowing energy? And so we're talking about, we want to incrementally take some of this power and transform it into electricity, is basically where we're headed here. And so in practice, what that means is we are going to extract head. Right? We're going to use machines to extract head. Okay? We depend on the flow rate to manage the timing. Right? So the flow rate part of the moving energy is quite manageable in terms of the temporal availability of that head. The conversion to electricity comes out of the extractable portion of that head. And we've already seen that's made up of three components. So we can extract energy from elevation. So the delta simply means a change. So we can change the elevation, we can change the pressure, and or we can change the velocity. So those are the transformations that are occurring, and when that occurs is largely mediated by how we manipulate that flow rate part. So the transformations are relatively straightforward, I suspect, in your experience. So we have thousands of years of using water wheels, okay, to take the linear movement of water. So here, this is a flume, a wooden flume that's delivering a linear stream of water. That water then interacts with this rotating wheel, which then converts the linear motion of the water into shaft rotation. The water drops off down the bottom. It has lower energy now, but it flows away. And we've transferred some of the energy in the flowing water into shaft rotation. And then that shaft rotation is used as mechanical energy for many, many different purposes. This happens to be a very old mill where inside that mill, mechanical, it was all done by pulleys and shivs and various gears to use the mechanical engineering directly. Now, of course, as you know, we put a second machine on that rotating shaft, which is a generator. And so we take the shaft rotation energy that we've extracted from the flowing water, and we convert that into electricity. Okay, so that's the machinery of energy transformation. I'm going to say more about that in a little bit. I do think it's worth elaborating a little bit on some of the history. So we know from archaeological evidence that humans have been building water wheels for at least 4,000 years globally. So humans pretty early on, not super early on, but pretty early on, deduced this important energy transformation of converting the flow of water into shaft rotation. One of the ironies I particularly appreciate is some of the oldest sites that shaft rotation was used to lift water out of mines, right, to dewater mines, and it proved to be a very effective technique. And like I say, it's spread globally. So there are archaeological sites around the world. And it really wasn't until the latter portion of the 19th century until hydropower evolved. And so for this entire thousands of years, most of the industrial energy in the world was in fact hydropower in the form of water wheels. Right? And so there's quite a history there of the relative role of water wheels that spread across the globe. Then in the 1870s, and the documentation here is a little tricky on a global scale, but we know that in Europe, it was recognized that we could take a DC dynamo and stick it on the shaft of a water wheel and get that extra energy conversion. And so the first small hydroelectric facility was in Germany in 1876. Okay. In the US, the first known documented implementation of hydroelectric power was in Michigan, okay, where a brand new energy utility stuck a DC dynamo on the water wheel that was used by the Wolverine Chair Factory, which is one of those factories that had a water wheel that was running all of the belts and pulleys inside. And they were able to demonstrate the second energy conversion, and they were able to light a number of street lights. And so that was really when this started in the US. If we continue on US history, the first dedicated hydroelectric plants, in other words, not just a retrofit on a mechanical energy factory, was in 1882. And Wisconsin and Minnesota still fight over exactly which one first generated energy. But either at St. Anthony's Falls, which is a photograph here, which is a natural waterfall, or in Appleton, Wisconsin, a small dedicated hydropower plant went online. And I think one of the important context here is that was literally almost at exactly the same time as the first thermal plant went online. So the development here has some parallel steps going along. If we follow through time in the US, we find that hydropower peaked in the 1940s. 1940s, 40% of capacity, of electrical capacity, was hydro. Right? That has declined very, very substantially. And so in 2020, we're down under 10% of capacity. This is not production, but capacity. And it has stabilized at around that role. I'll try to elaborate a little bit more on that in a second. And the latest, much more recently, is the development of hydrokinetic energy sources. I'll say a little bit about that, and you'll hear more about that in a later lecture. So I'm going to show you some data. You've probably seen much of this, but just to keep some context. So here we have primary energy consumption 2022, and what you can see is that renewables were 13%, and within renewables 18% was hydropower, and if you multiply 18 by 13 you get 2.3%. So it's a pretty small sliver of the US energy resource, right? But as we'll see, it tends to be a very important one. The story globally is very different, okay? And so it's important that we take a global perspective. So here we have a timeline by decades over the second half of the 20th century and into the 21st. And these are by decades, each of the set of bars. On the left-hand side, we have capacity, okay? And that refers to the two bars, okay? The white is the added capacity in that decade, and the blue is the cumulative capacity. So you can see that in the US, the cumulative capacity flattened way out very quickly, but globally, the installed capacity of hydro has been increasing very, very substantially. Okay? The green, which goes on the right-hand axis, is the average annual generation in terawatt hours, and you can see that that is a sharply upward trajectory as well. So the global picture is quite different than the US picture. So if we look at the global distribution among resources, hydro this was 2022, so the same year, about 15%. Right? Hydro varies because, of course, it depends on the availability of water, which is a highly variable resource in itself, right? But globally, in the ballpark of 15%, so a much bigger number than in the US. And it's kind of fun to see where that global resource is. So here we have a pie chart of the top 20 nations of installed capacity, and it's color-coded by continent, okay, just to give you some idea. So we can see the red color is Asia. Here we have South America, North America, sort of classic continental Europe, and then Central Asia and South Asia in the purple there. And so you can see it's a broadly distributed resource dominated by China and South America and North America. Okay. So one of the fun things about hydropower is this global nature of its role in the grids across many, many different countries, cultures, governments, societies, and economies. And economy is an important one. And so I think it's to fully appreciate hydropower, we need to have to look at this plot. We could argue about this for a long time, but what we have here are the 17 countries, okay, that are dependent on hydropower for at least 90% of their resource, okay, of their electricity supply. So these are the countries that really, really depend on hydropower. Okay? And then on the vertical axis is the United Nations Human Development Index. I don't know if you're familiar with this. It has three components. It has health and life expectancy, it has education, and it has standard of living, kind of mushed together into an index. And they're ranked. One is at the top, and 187 is at the bottom. Okay? And what I think you might find interesting here, the number one ranked, which is Norway, all right, is extremely dependent on hydropower. Right? But you see very quickly as we look at these countries, all of which are mostly dependent on hydropower, we quickly drop down into the bottom tier of this HDI ranking. So in other words, into the less developed world. We'll just sort of leave it in that language. So hydropower is integrated with sort of the socio-political environment and the economic environment in ways that some other resources are not. But this is an important context to keep in mind as we go along. It's a global industry, and the focus of the global industry is clearly not on the US, it's on these countries that are incredibly dependent on hydropower. A few other little tidbits about hydropower. Here we have a map of the 20 largest power plants by capacity, not by production, but by capacity globally. Okay? The capacity is indicated by the size of the circle. The little symbol indicates the primary energy source. And what's you might find interesting, what I think is telling here, is that the top 6 of these are hydropower facilities, right? And 11 of the top 20 are hydropower facilities. So hydropower plays a distinctive role in developing economies. They also are very large powerhouses, okay? And so we can think about the consequences of that as we go along as well. One last little contextual piece that I'm going to go back to the US for data is who owns and operates hydropower facilities. This is also another important characteristic. So on the left, we have a pie chart of the total number of licensed hydropower plants. Right? So it is simply a count, right? And the color coding is based on whether it's owned and operated in the private economy or in the public economy. Right? So blue, as you can see, are investor-owned utilities, wholesale power market, industrial. There are a lot of industrial hydropower plants. So you can see about 2/3 of the plants are owned privately. The other third are owned publicly, and the two colors here, just to get a sense of how scale plays into this, the darker represents federal government, federal agencies that own and operate hydropower, and then the lighter red represent other scales of public ownership and operation. So a third of the power plants in the US are government owned and operated, and 2/3 are private. Right? The picture gets even more interesting if we look on the right, which is the capacity of those plants. Color coding is the same, right? And so what we can see is that those 1/3 approximately of publicly owned hydropower facilities make up 3/4 of the capacity. Right? And what you can think about, we'll talk about this more as we go along, is that if a hydropower plant requires a large dam, for example, right? And typically the private economy doesn't have access to the resources to be able to construct such a large facility. And in addition, in the US, the government owns all the water. Right? So that adds another piece to the story of why we see these particular pie charts. So hydropower has a lot of interesting socio-political characteristics that come up over and over and over again in a variety of different contexts. And we'll come back to some of those as we go along. But let's talk about facilities, so we have a better image of what some of these things look like. And so we have our power equation, we have our head equation. We're going to try to extract some of this head. And there are really two design variables that drive all hydropower facilities. One is the flow rate of the water, the volume of water flowing per unit time. Okay. And in general, in hydropower facilities, the flow rate is about timing. Right? It's about when we are able and want to extract energy from that flowing water. And so what that means is that the flow rate part of hydropower is relatively easily manipulated during operations. So the flow rate is an operations variable. On the other hand, the head, okay, the head right here, all right, offers a tremendous range of management options, but it's typically selected and design in the design stage. So it's a design decision. So we have some decisions that are based sort of at the beginning of a project, which is the head. And then we have other characteristics that are operational after we have the facility and allow for a different kind of flexibility. And we'll see how that plays out in a second. So there are lots of ways that people try to classify hydropower facilities. Right? There are two broad classes. Right? One is conventional, right? Kind of boring, and the other one is hydrokinetic. Okay, that sounds more exciting. And I'm going to say just a little bit today about hydrokinetic. You're going to hear, I believe, next week, there's a growing interest in extracting energy from moving water in the oceans. Okay. The other area of hydrokinetic development falls under the broad category of ambient flow. And so I don't want to spend a lot of time on it because we don't have enough time, but I want to just give you a sense of what that means if you encounter that term. So the idea of ambient flow as a hydropower resource comes about because we move a lot of water around in pipes. Okay? And it turns out often we have more energy in that moving water than is needed to move the water. Right? There's excess energy. And so what's been happening in the last decade or so is that a number of developers are building tiny little turbines that you can install in a pipe and extract some of the energy as the water flows by in the pipe. So you can take the excess energy out and convert it into electricity. And so there's a lot of retrofitting going on right now. There's a good bit actually happening in California because a lot of water comes out of the Sierras at very high elevations. It has lots of energy. It has more energy than it needs to be able to deliver that water to us and to irrigators and to industries. And so a number of water utilities are looking into putting a small turbine with a generator attached into those pipelines so that they can use that energy as an electric resource rather than just having to dispose of that energy in one way or another. Okay? Stanford actually has to do this. Our non-potable water comes from relatively high elevation in the Santa Cruz Mountains, right? Foothills. It has more energy than is needed to get that water to campus. And so when the water gets to campus, it has too much energy for some of our sprinkler systems. And so we have to, the term is a term of art in the water business. You have to burn off some of that energy, which basically means you find some way to take some of that energy and get rid of it non-productively. And there are many different devices that do that. But we're moving in the direction of trying to extract electricity from that moving water. I'm going to spend most of my time talking about conventional facilities. And there are different ways that people classify conventional facilities. I'm going to focus on what I've called here configuration. So there are different configurations that are used to do this energy conversion process. So let me run through a few of those, and I'm going to use a photo for each to try to give you a sense of some of the similarities and differences. So here we see a run-of-river facility in Alaska on the Tasmania River. And what you see is that we have a geologic impediment to the river such that we have the Tasmania River falls, and because of this hard rock, we have a waterfall. So we have water at high elevation and water at low elevation. The difference, this has more energy. Remember, that's Z, all right? It has more energy. That energy is dissipated naturally by going over the waterfall. It's aerated, it sprays. That's actually a disposition of energy. You create all currents and mixing in the water below. So all of that is essentially burning off the energy difference between the water up here and the water down here. What they did here is they put an intake and they take a small fraction of the total flow of the river, and instead of having it go over the waterfall, they have it go through a powerhouse. And in that powerhouse, some of the energy in that flowing water is converted into electricity, and then the water is discharged at that low elevation at the energy below the waterfall. Okay, so it's run of river because we're not manipulating the flow in the river at all. We are manipulating whether it goes over the waterfall or goes through the powerhouse, but that's the only manipulation. Okay, and we're not storing any water in the system. We're taking the water as it comes and as it moves by. And in the hydropower world, that's referred to no pondage. Right? So there's no pond anywhere that represents stored water, which is stored energy. And so we're just taking the flow as it comes. And that's because this is a small powerhouse. It's only using a tiny fraction of the total flow. Right? So this is a run-of-river facility with no pondage. Here's a run-of-river facility that is somewhat different in appearance. We don't have a waterfall, so we built one. Okay? So here we see the Ice Harbor Dam on the Snake River, which is a tributary of the Columbia River in the Pacific Northwest. And so you can see the waterfall right here. So a big chunk of the water is going over what's called the spillway and being delivered downstream, and energy is being dissipated by all this foam and action in through here. But a portion of the flow goes through this building, which is the powerhouse. So some of the energy in the flow is being converted into electricity. Only a fraction of the flow is going through. And even though this is a fairly substantial dam, given the size of the river, the reservoir that's created upstream is very small. It may not look like it to you, but it is in fact very small. Right? So it has pondage, but it is run of river. Right? And what pondage means here is that, so if we store water on the upstream side of our powerhouse, we're storing energy. Mm-hmm. And so the pondage here the time scale of storage is days to a few weeks. Okay? So we're time shifting. So for example, it's very common here to store some water on the weekends and then use that water on weekdays because there's more grid demand on the weekdays than on the weekends. So we store a little bit of energy, but not a lot, to allow us to do a little time shifting. Okay? So we have Tazamita Falls, run-of-river. We have Ice Harbor, run-of-river. Here's my third run-of-river example. Okay. This is a micro hydro facility. Okay. But it's the same basic concept. You can see the pipeline right here. So out of the picture upstream, we have a small stream right here, bubbling over the rocks as it goes its way downhill. And a small portion of that water is diverted out of the creek or stream into this pipeline because the pipeline is much smoother than the river. Right? That water gets down to this location with more energy than the water in the channel. Right? And so that energy difference is used to turn a small turbine and generator. Right? This is a one household micro hydro facility. Right? But it's the same idea. It's a run of river. We're not trying to store energy. We are just taking advantage of the higher energy water upstream. Okay? So these are all examples of run-of-river facilities. The other end of the spectrum are storage facilities. And so I thought we'd go big for this one. So here we see, this is Libby, which is on the Kootenai River, which is a tributary of the Columbia River. So just like the snake. And so what we see here is that we constructed this large barrier, Libby Dam. There's a substantial powerhouse right here. Here's the spillway. No water is being released now. And that's because all the water that's coming in is being stored. Okay? And that stored water is stored energy. And so if the inflow is greater than the outflow, that means we are adding water to storage. If the outflow is greater than the inflow, we're taking water out of storage. So the operations here, remember that's the timing part, the operations can make a decision about when to release water, how much of that water should be released through the powerhouse. And so it allows for a grid management opportunity in terms of the timing of converting or extracting some of the energy in that stored water. Okay, so this is a storage facility. Now, whether run-of-river or storage, there are sort of two basic ways these work, and you've seen examples of both. So Libby, we just looked at, is an example of where we don't take water out of the channel. Right? We leave the water in the environment, in the channel, but we create a reservoir by building a barrier, the dam, and then we divert that water through the dam, through a powerhouse, and then release it downstream. And so many conventional facilities have this structure. The other structure is an example, that micro hydro I showed you, where we take water out of the channel. So we actually divert water out of the channel. That has very different impacts than blocking the channel and creating a storage. We'll say a little bit more about that when we get there. We take water out, and then we find a way to deliver that water much more efficiently in terms of its energy than if it stayed in the channel. If it stays in the channel, it has to flow around rocks, over logs, and so that dissipates energy. If we put it in a pipe, the pipe is designed to minimize the energy loss for the flow, and so we end up with water down here. We put a powerhouse down here at a lower elevation. It's the water that came out of the stream. It's now here with more energy. We extract that excess energy and convert it into electricity and dump the water back in the river at the energy of the river. So there are these different ways we can organize how we manipulate the hydrologic environment in order to accomplish our energy goals. Okay. There's a third category of hydropower that I'm sure you've heard about. It gets plenty of press now and then, and that's called pump storage. Okay. This is an explicit acknowledgement, right, that stored water is stored energy. Okay. And so how pump storage works takes advantage of the fact that the machines that we use, so the turbines and the generators, right, have direct analogs. So a generator looks just like a motor, very similar to a motor. And a turbine, many turbines, not all, but most turbines look a lot like a pump. So we can build a machine that can be operated in both directions. We call it poetically a pump turbine and a motor generator, okay, like our hyphens. But what we do is we take advantage of a situation where we can have a lower reservoir, a lower storage, and an upper storage, upper meaning higher elevation, more energy. Right? And what we can do is when there's excess energy on the grid, and this has become even more interesting now as we add more and more intermittents, okay, that are also tend to be intermittent at several different time scales. When there's excess energy on the grid, we take that energy and we put it into the water by raising it up into the upper reservoir. Then, when we would like to return that energy, if you will, to the grid, we just operate the machines the other direction, and the pump becomes a turbine, and the motor becomes a generator, and we put energy back on the grid. So we store energy as water. We take advantage of highly efficient machines. Pumps and turbines are extremely efficient energy converters, and we are able to have large-scale energy storage. There are lots of ways we can do this, and so just so you've seen the words, I'm not going to go through all of them, but there are open-loop systems, there are closed-loop systems, but it's basically something like this. We have an upper reservoir, we have a lower reservoir, and we have a powerhouse that moves water both ways. Let me illustrate with a few images, the photos that make it a little more obvious. So here we're looking straight down at a dam. You might recognize this as a dam. This happens to be on the Coosawattee River in U.S. state of Georgia. Okay. It's federally owned by the Corps of Engineers. Right? Here's a powerhouse. Here's the entrance channel. So the water goes into the powerhouse from here and it goes down there. And it turns out this powerhouse has pump turbines and motor generators in it. Okay. And so this is the reservoir. So this is upstream. And then downstream, we see this area down here. And it turns out, if I put everything in the same photo, you can't see anything. But down here is a little small low dam, right, that doesn't store a lot of water, but it stores some water. And so what's done here is water is released through the powerhouse into this lower reservoir, and then it's pumped back up, right, to do pump storage. Right? So they literally have two dams, a big dam and a little dam, right? So two reservoirs, and water is moved back and forth, back and forth, back and forth to help manage the grid in the Southeast. Right? So in the vocabulary of this world, it's a pump back, open loop pump storage facility. Here's another one I thought quite different, but on the other hand, conceptually the same. Right? This is the Ludington pump storage project. This is an off-stream open loop facility because the upper reservoir doesn't have a river flowing into it. Right? What they did, they took advantage of Lake Michigan, very large lake, all right? And they literally excavated a pond at elevation along the shore of Lake Michigan, We have a powerhouse that has pump turbines, motor generators, and so they use Lake Michigan as the lower reservoir. Excess energy, water is pumped into the upper reservoir. When that energy is more valuable, it is released back down into Lake Michigan. So there are many different ways of configuring pump storage. Here are the existing pump storage facilities in the US. We were just looking at Ludington. That's where Ludington is, there on Michigan. Right? Carter's, the first one that I showed you, is down here. Right? The largest in the US right now is Bath County in Virginia, which is 2.1 gigawatts. Okay? It's a big, big facility. But you can see there are pump storage all across the country of wide range of scales. Some of them are quite small, and some of them are quite large. Interestingly enough, Europe has been developing pump storage much longer and much more intensively than the US, just to give you, I want to sort of bring you back to a global scale here. So here's a timeline through from 2000 to 2020. The dark portion is the US cumulative megawatts in pump storage, and the blue is Europe. Right? So Europe has invested much more in pump storage than the US has. And you might want to, you can sort of think about the nature of the European grid. The Europeans have a lot more nuclear power, for example, and nukes like to operate at a constant rate. So if you have a lot of constant rate sources, storage really is much more valuable. Plus they have these cool mountains, okay, like the Alps, that have big elevation differences. And they have such big elevation differences, you don't need really large reservoirs because you get lots of head. Right? If you ever have a chance to fly over the Alps and it's not cloudy, this may not happen in your lifetime, but it's happened to me once or twice. It's really entertaining to look down, because if you look down at the top of the Alps, you'll see at the top, you'll see these little blue circles and rectangles that look kind of like swimming pools sitting up on top of a number of the peaks or on ledges, all right? Those are the upper reservoirs for pump storage. They don't need to be big because they have so much head difference. Remember, we always have these trade-offs between volume and head, flow rate and head. And so Europe has invested much more heavily. Here is the global picture right now, more or less, of the pump storage, and we have operated, under construction. You got to be careful because this has planned and announced on it. From experience, we can assume that announced may or may not happen and planned may or may not happen. But the point is, the dark blue and the under construction ones exist. And here's that European density of pump storage. Right? Here's the US. You'll notice we have this swath along particularly the southeast and the Appalachians. And then we have scattered where we have lots of mountain relief in the west. And then China has been investing very heavily in pump storage. They've got elevation difference to facilitate it. And then India is starting to do more and more as well. So there's a lot of work going on into pump storage. Let's come back to machines now for a few minutes. And I want to talk a little bit about turbines, because to fully appreciate hydropower, you have to know a little bit about the machinery. And so we've been, as I've said many times now, we've been making turbines for a very long time. We are really good at making turbines. They are very efficient machines. Right? And they're all about extracting pressure and velocity. And so just to give you, I give you the fluid mechanical definition of a turbine. And then what you see here are some examples of different types of turbines. And as you can see, they look very different. Okay? There are three broad classes. There are impulse turbines. These are the closest things to those water wheels. Okay? They are essentially a set of buckets on a wheel. Reaction turbines operate very, very differently. They might look like this, or they might look like that. So we have many different kinds of machines, all of which are developed for the same purpose. and I've suggested all of which are very sophisticated. So the question is why? And the answer of why is right here in this complicated graphic. So what we have here is an area, a zone, that's made up by the flow rate, that's the Q, in cubic meters per second along this axis, and it's not a linear scale, so it's a weird scale. This is a European publication, and I don't know what they were doing, but it's sort of a logarithmic scale along here, and then on this axis is the head. And so this domain is broken up into chunks of area by these solid lines, right? And there's a little bit of illustration to explain why. So in simple terms, if we have a setting where we have a very high head, but a very relatively low flow rate, right? So think about those mountains like the Alps, where we have big elevation difference, but not a lot of water flowing, right? In that situation, you want to use a Pelton wheel. Right? That's the bucket one that's going around. On the other hand, if you have very low head, but lots of water flowing, you want to use something called a bulb turbine. Okay? The brass one that's going around is a Francis turbine, and that's kind of in the middle here. So we've been doing this for long enough that we know that that trade-off between flow rate and head leads to machines that are tuned to the combination in a given location. Okay, so we have a number of different kinds of turbines. There are only about 5 different turbine manufacturers globally. It's a very specialized business. And if I went in and said, gee, I want to put a hydropower plant here, they would ask me all these questions, and they said, all right, come back in a year and we'll tell you exactly how many turbines and what they should look like and how much they're going to cost. Right? So it's a very specialized business. When you buy a turbine, you get a hill curve. All right? So here we have another plot. We have flow rate now on the vertical axis, and we have head on the horizontal axis. And then we have these lines of equal efficiency. And that's why it's called a hill curve. Those lines of equal efficiency look like elevation contours. Looks like a contour map of a peak. Right? And so there's lots of labels on here. Not going to worry about most of those. But if we imagine these are lines of constant efficiency. So in other words, is we look at for a given machine, we can operate it at different heads and different flow rates. What we would like to do is operate it right there because that's the top of the hill. Right? At that point, it is most efficient. Right? But what's interesting here and important is that you'll notice that the hill is elongated horizontally. Right? And so what that means is that a given turbine maintains its efficiency more effectively if the head varies than if the flow rate varies. Okay? And the bottom line of that is that many hydropower houses have more than one turbine. Right? And it's because if you are dealing with a range of flow rates, rather than operating one turbine over a bunch of different flow rates, which would result in moving this way on this plot and losing efficiency, you have multiple turbines, and you turn on the number of turbines you need for the flow rate you want, and try to keep those turbines operating at their maximum efficiency. So if you visit a hydropower facility and you see multiple turbines, it's essentially about this hill curve, about the nature of the efficiency. We got machines, we got the basic physics. We what I want to do now is think about what this means about how hydropower facilities are operated and their role on the grid. Okay. So first of all, because energy available for hydropower is dependent on water availability, and water can be highly seasonal. It can vary dramatically from year to year. We may or may not have a lot of storage. And so what that means is on a given grid, and remember, think about countries that are almost entirely dependent on hydropower versus countries where hydropower plays a relatively modest role. Some grids, hydropower operates in the base, right? And other grids, it operates as a peaker. Right? And in some grids, part of the year it's a base, and part of the year it's a peaker. Right? So thermal utilities that have thermal facilities love having hydropower with their thermal facilities because it gives them a lot more flexibility on both sides in terms of how the thermal is operated, but also in how the hydro is operated. So that's one aspect of hydro operations. An extremely important aspect of hydro operations are ancillary services. Hydropower is great at ancillary services. Okay, and so, for example, there are a number of hydropower plants in California that 9 years out of 10 make all of their income from ancillary services. They sell almost no primary energy. They just deliver ancillary services. And to illustrate a little bit about why that is, this is a messy plot from EPRI that I didn't create, but what we have here are a number of ancillary services. Okay? And then we have a number of different sources. So here we have sources that are synchronously connected. Here we have the inverter stuff. All right, so this is PV, wind, battery storage. And then here is another column recognizing that we also can manipulate demand to at least deal with some ancillary characteristics of the grid. But what I wanted to draw your attention to, so this is the column for hydro. Okay? And the scale here, as you can see, is relative comparison of reliability contributions. Basically, if it's all green, it's really good at that ancillary service. And if it's this sort of glowing black, it can't provide those ancillary services. And so what you see with hydropower is that it is a dominant provider of almost all ancillary services. Okay? And the two I wanted to really highlight are frequency control. Managing droop, hydropower is great for that. Right? And that's because all you have to do is open a valve and close a valve a little bit, and you can alter the rotating speed, and so you can manage the frequency. It's a synchronous generator. But the really big one is down here at the bottom, which traditionally is called black start, which means if your grid goes down, you can power it back up. Okay? And thermal plants take a very long time to get back online. Almost any, and of course, if you have a power failure at night, you don't have any solar, you may or may not have wind, those are highly intermittent. And so most hydropower facilities right now have their contract with their utility. One of their resources that they provide is black start capability, because all you have to do to start up a hydro plant is open a valve. Right? And so typically a hydropower plant can be synced online in less than 20 seconds, okay? Sometimes faster. So ancillary services are a very, very big deal. Okay? And then the third piece that I've sort of been hinting at in various ways, but I want to say a little bit more about, is about energy storage. Right? So primary energy resource, ancillary services, and then energy storage. Right? And we've talked about pump storage, which is a very explicit manipulated storage of energy in water. But if you think about it, anytime you store water, whether you pumped it there or whether it just came in from the river, you're storing energy. Okay? So hydropower has the potential for very substantial energy storage. And to give you some sense of that, I have a few little graphics here. So here we have another one of these sort of generic plots of the capacity that's available for storage and then the release time. Okay. And what we see is that pumped hydro, which they don't even put regular storage on here, but pumped hydro is this big swath out here. And relative to many, many other sources, we have more capacity and longer release times. Right? And so that's one indication of why storage is so important. I just thought this might be fun to look at and see how this was from last April, and it's literally it's over just a 1 month summary, and you can read all the labels, but I would draw your attention to hydro here to see how hydro is operated. So what you can see is that hydro releases go up, all right, before the sun comes up to meet early demand. Right? Then hydro basically stops delivering and starts storing water, which means storing energy, so it's available to pick up this nice little lag after we lose solar in the day. So the being able to accommodate intermittence takes big advantage of the ability to store energy on both short time scales and long time scales in reservoirs. Here's another, this one is somewhat more self-serving by the hydropower industry, but here we have some scaled information. And so again, I will point out, this is from the International Commission on Large Dams, so there is an axe to grind here, but the data are useful and relevant. What you can see is that what they've tried to do is to scale the amount of energy storage associated with water storage behind large dams. So the big box here represents the water that's stored behind dams that represents stored energy. And if you make some assumptions and approximations, it's 1,500 terawatt hours. That's a lot of energy, all right? This box down here, and so these are intended to be scaled. So the dark blue is, that stands for pump storage. So pump storage hydropower is about 8.5 terawatt hours relative to this larger scale storage in reservoirs. Right? And then this is where they're trying to make their point. This little box right down here are batteries. Now the battery box has grown some, even since this was done. It's still very small compared to the blue boxes. So hydropower still plays a major role in energy storage for grid management. That's sort of the bottom line. So we're back to my summary. Right? Hopefully some of this now makes sense. It is renewable. Right? It's solar energy, essentially. Right? It's highly efficient. We've been doing it for a very long time. It's cold. It doesn't involve heating and cooling. And so the machines are very, very efficient, and because we've been doing it for a very long time, highly scalable. The variable costs are very low. We don't buy a fuel, right? We pay the consequences of our fuel, but we don't buy the fuel, okay? They last a long time because they don't heat up, so they stay cold, which means the metals last a lot longer. And we've already talked about energy storage and ancillary services. On the other hand, if there's no water, there's no energy, right? So it's not fully dispatchable. You can't put a hydropower plant wherever you would like, right? And you can try, but you can't. And so there's limited constrained siting, and usually there's high transmission costs associated with a new hydropower facility. They're not standardized. right? So you can't go on Amazon and buy a hydropower plant. They're very, very site specific. So they tend to have significant design costs, okay? And then what I really want to talk about for the last few minutes is a little bit about the impacts, because they get a lot of attention, rightly so, and I want to try to contextualize that a little bit. Okay, I'm going to break this down into two pieces. We're going to think about the impacts of the generation process itself, right, versus the impacts of building a dam and a reservoir. Right? Because we build dams and reservoirs for many, many, many reasons, many more than hydropower. Right? And so I think it's useful to compare, to sort of factor those out a little bit. So if we think about the impacts of having a hydropower facility on a river, okay, one significant impact is downstream organism passage. Right? And so what we're talking about here, this is a little cartoon. These are supposed to be little salmon. Here we have a powerhouse. And here we have a poetic listing of all the things that happen to fish as they go through a turbine on their way through the powerhouse. Right? It's a very, very challenging environment. Okay, and so I'm not going to try to define all of these things, but all of them are very, very hard on fish. And so there's mortality and injury associated with downstream fish passage, so fish going downstream. And if you look closely at this, you will notice that these fish all are facing upstream. And that's because many, many migratory fish, particularly if they're anadromous, so they spawn in freshwater and they grow to adulthood in saltwater, when the young of the year are moving from freshwater to saltwater, they go tail first. They don't swim. Right? They go with the current. So they don't even see what's coming. Okay? And so they actually go through all of this tail first. It's probably better for them, but in any case. Turns out we know quite a bit about this, so I just thought I should mention. There have been a number of tools developed to try to monitor what happens to fish when they go through turbines. And then there have been a number of approaches to try to figure out how to mitigate some of that cost. So there are tags, and we now send robot fish through turbines to see what happens to them. So it's become a relatively sophisticated business. The industry has developed lots of screening schemes to try to keep the fish out of places where it's not good to go and try to get them to go to safer places. There has been, in the last 2 decades, a lot of work done on redesigning turbines to make the experience of going through a turbine not be so hazardous. Right? It depends on the manufacturer and their labels. So GE, which is a major maker of turbines, they now have fish-friendly turbines. If they were being honest, it would be fish less unfriendly turbines, but they call them fish-friendly turbines. And then another label that's often used are advanced turbines. So they redesign the moving parts of a turbine, trying to address the hazards for fish passage. Turns out what they've learned, which is a bit of an irony, is that when they redesign the turbine runner, that's the moving part, to better accommodate fish passage, it actually gets more efficient. So they discovered new efficiencies in turbine design by trying to not kill as many fish. All right? So you can think of that, I guess, as a win-win, and certainly the turbine industry does. Okay. Well, I wanted to give you a little bit of data. And so here's one example. I just picked it because the data were readily available, and it's a well-known study. It's on Rocky Reach Dam, which is on the Columbia River in Washington. and it's looking at the downstream migration of juvenile sockeye salmon. Okay, and so there are, what you can see here are there 3 ways that fish can get by this facility. They can go over the spillway. Right? In other words, they can not go through the powerhouse, but go over that waterfall that we saw. Right? They can go through the turbine. Right? Or, in this particular facility, has something known as a surface collector, which tries to capture the migrants and put them into a passageway that does not go through the turbines, but gets them safely downstream. And so this is a sort of a blow up. The way you know the surface collector is working, this is the outlet of the surface collector. And so when there's downstream migrants and they're actually using the collector, it's really fun to go there, and because you can see fish flying out of the end of a pipe, right? So they come flying out back into the river alive, which, as you can see, survival rates, the 95% is not considered good, by the way. But you can see that there are different levels of survival, and you can see half the fish went through the turbine in spite of all these efforts to keep them to not go through the turbine. There's been all kinds of interesting research on if you play loud music, will young fish move in one direction or another? So there's a whole literature on what kind of music moves fish more efficiently, and they try flashing lights, all kinds of things to try to keep the fish from getting themselves killed or from us killing them. All right, well, that's the obvious dominant issue is fish passage, but there are some other issues that it's worth noting, and that is when you operate a facility for hydropower with all this time shifting, there are impacts on what the downstream looks like. And just to sort of overemphasize that a little bit, here is 1 week worth of data, and what this is, I'll just pick one that's easy. This one is the water surface elevation of the river downstream of a powerhouse. And what you can see is that every day the water level goes up and down and up and down and up and down. That's not a natural pattern. And the ecosystems there haven't evolved for that kind of a pattern of variability. So there are impacts on more than just the fish. They're dominantly downstream. The impacts of dams and reservoirs is a much, much, much longer list, and I don't have enough time to go through those in any details. I'll just sort of show you that I've tried to list them in a relatively digestible way in a set of slides. There are all kinds of interesting issues, and so I think I will just stop right with the last 2 slides here. I encourage you to take a look at that or take a course on dams and reservoirs. But here is another look at hydropower more broadly as to where we're headed. It's a different organization, and it sort of presents it a little bit differently. The previous map I showed you was just pump storage. This is hydropower. And so you can see the big development is largely in East, South, and Southeast and South Asia right now. Not a lot going on in the US. And Africa is another major target. This is reflected, just so you know what this plot is, this is an age profile of installed capacity. And it's worth comparing North America to China, for example. And the color scale goes from young to old. And so you can see that North America is dominated by older facilities. And so there's a different future ahead for North America than in Asia and East Asia. So that's it.